In the previous video, we had a brief idea of hypothesis testing. Actually, the entire process of a hypothesis testing includes the following steps. So in the first step, we need to set up an appropriate hypothesis. And in the second step, we have to specify the test statistic and the model. And then we need to find the rejection region and make our final decision. So we're going to take a look at those steps one by one. So the first step, how to set up an appropriate hypothesis. Actually, there are a lot of ways to set up your null hypothesis and alternative hypothesis. So in this class, we're going to introduce you the simplest way. Okay, so we're going to start with our initial guess, or we call this initial claim. Okay, for example, so my claim is the average number of vehicles pass through a junction in an hour is at least 45. Okay, so this is my claim. My claim is that the average number of vehicles pass through a junction in an hour is at least 45. So my claim, remember we have discussed before that we are interested in the population parameters instead of sample statistics. So in here, we're interested in the population mean, right? So I'll use lambda to denote the population mean here. So lambda is at least 45, means lambda is larger or equal to 45. Okay, so with this claim, you can write down its opposite way. So its opposite is, so lambda is smaller than 45. Okay, now you have your claim and then you have your opposite opinion. So I'm gonna write lambda is equal to 45 here and set up this one as my null hypothesis. See, I'm gonna find where the equal sign is and set up this one as my null hypothesis. And the opposite side is just my alternative hypothesis. Okay, so the basic rule is to find where the equal sign here. Okay, sometimes your claim is, say, for example, my claim is the average number is larger than 45. Okay, so the opposite side is lambda is smaller or equal to 45. So what I'm going to do is to find the position of the equal sign. Okay, in this case, the equal sign is here. So I'm going to set this one as my null hypothesis, and its opposite side, which is our original claim, as my alternative hypothesis. Okay, so this gives us that my H0 will be the parameter of interest is equal to something, say lambda 0, versus its alternative hypothesis is lambda is not equal to lambda 0, or lambda is larger than lambda 0, or it could be lambda is smaller than lambda 0. Okay, but actually if you take some other like advanced statistical courses, you're going to find my null hypothesis could be something like this. Could be lambda is larger or equal to lambda 0, or smaller or equal to lambda 0. It doesn't have to be like exactly equal to something. It could be larger or equal to or smaller or equal to, but it doesn't matter. Okay, it really depends on what your alternative hypothesis is. But in order not to confuse you, like because we're taking an intro level course, right? So for the sake of this course, I'm gonna set up my null hypothesis as the parameter of interest is equal to something. Okay, so in this course, we're all gonna set up my null hypothesis as the parameter of interest is equal to a constant. And then versus the alternative hypothesis that, say, your lambda could be not equal to this one, or larger or equal to this one, or larger than this one or smaller than this one. It really depends on the context, okay? So I'm going to repeat this rule again. Okay, so in this class, I'm going to set up my null hypothesis as the parameter of interest is equal to something, okay? But to be more specific, I'm going to start with my claim, okay? So if my claim is, like in general, we say theta is the parameter of interest, okay? Parameter of interest. And definitely we can have its corresponding sample statistic, say, theta hat, okay? So, as we discussed before, our claim will focus on the parameter of interest instead of the sample statistic. So we're going to focus on theta, okay? So if my claim is theta is larger than theta 0, so you can write down your opposite side. Okay, so your opposite side will be theta is smaller or equal to theta 0. Okay, and then you find the equality, okay, and use it as your null hypothesis. So it's going to be, I'm going to write it here, okay, so it's going to be, my null hypothesis is theta is equal to theta 0, and versus, since you have taken the opposite side as your null hypothesis, which means the opposite side of the opposite side, which is your original claim, will be your alternative hypothesis. Okay? On the contrary, if your original claim is, say, theta is larger or equal to theta 0, so you will have your opposite side of your claim is theta is smaller than theta 0. Okay? And I will find where the equality is as my null hypothesis, which means the opposite side of the null hypothesis is my alternative hypothesis. So my alternative hypothesis will be theta is smaller than theta 0. Okay, so that's the basic rule of setting up an appropriate hypothesis. Okay? All right, so that's the first step. All right, so I will give you some more examples. For example, say my claim about the sample proportion is P is larger than 0.5. Okay, so its opposite side would be P is smaller or equal to 0.5. So my HO would be, first of all, find where the equal sign here. Okay, so it's P is equal to 0.5. So its opposite side, which means the alternative hypothesis, is the opposite side of your chosen statement. Okay, because you have chosen this one, so which means its opposite side will be your alternative hypothesis. Okay, so that's how do we set up a appropriate hypothesis. So the next step, we need to specify the test statistic and the model. Okay, so what is a test statistic? All right, so I will have to make sure that we have enough space to write it down. Okay, actually, a test statistic is a function of the observed sample information on which the decision to be based. Okay, so this means it does not include the population parameters of interest. Okay, for example, we're interested in the sample mean, which is mu. Okay, so for example, my null hypothesis is mu is equal to mu 0 versus, say, mu is larger than mu 0. Okay, so we're interested in this mu. But as we discussed before, in reality, we cannot know this. Okay, but we can draw a random sample and we can have the corresponding sample statistics. For example, we can have the corresponding sample mean. Okay, and our goal is to use the sample mean to estimate the population mean, which means your sample mean should not include any information about, like, you cannot include the exact value of this mu, right? So it's not a function of mu. So mu should not appear in X bar. This makes sense, right? Okay. So another example could be like the p hat we have discussed before. Okay. So the population proportion p is equal to 0.5, and its alternative hypothesis is p is not equal to 0.5, say. Okay. So my sample proportion, my sample statistic could be this could be the sample proportion, p hat. Okay, so p hat cannot include this p because we need to use this p hat to study this p. Okay, we need to use this p hat to study this p. So we should not let this p be included in this p hat. Otherwise, like, we cannot do this, right? Okay, so that's the second step. The third step is to find the rejection region. Okay, so what is the rejection region actually? Now we have set up the appropriate hypothesis and we have chosen the sample statistics. So in the third step, we have to define our region of interest. So in this video, we're going to introduce you the brief idea of the rejection region. Okay, for example, we have set up our null hypothesis. Suppose that we are interested in the American adults, the average height. Okay, so my null hypothesis is that, let's say my mu is 5'6". Okay, I just randomly write a number. Okay, so this is my null hypothesis. And according to some reference, my alternative hypothesis is mu is larger than this value. Okay, for example, it could be 6. It could be something else. Okay. All right. So this is my mu 0, right? So my HO is mu is equal to mu 0 versus mu is larger than mu 0. Okay. And in order to study this population average, which is the population mu, okay, so the population mean, mu, okay? So I'm going to choose the sample statistic, X bar, to estimate this mu. Okay, so this is my test statistic. This is my test statistic. And I'm going to create a rejection region to decide whether HO is correct or the alternative hypothesis HA is correct from a probability point of view. Okay, so because we know that this X bar, the sample mean, will always follow a normal distribution with mu and sigma square divided by n according to CLT, right? Because, for example, we can let the sample size n is larger than 30. Say we take n is equal to 40. Okay, we can apply CLT, and that's what I always said. Okay, so normal distribution probably be one of the most important distributions of all time. This is because of CLT. Okay, once you have the central limit theorem, all the corresponding sample mean could follow a normal distribution approximately, okay, as long as the sample size is large enough. All right, and we also have the probability that, the mean of x bar is exactly the same as the mean of the underlying distribution x, okay? In this case is the height of a molecular dose. All right, so I'm going to use this distribution information of x bar to decide which side is correct. All right, so we have a plot about x bar. All right, so this is the value of x bar, and this is the value of its PDF. Okay, if H0 is correct, then its PDF will look like this. All right, and it's a metric with respect to this true mean mu, the one that we're interested in. Okay, so this is mu. Okay, so if H0 is correct, which means my mu is equal to mu 0. So this is mu 0, and this is my H0. Okay, the PDF curve of my H0. However, I'm going to just extend this line a little bit longer. Okay. All right, so if you cannot prove that H0 is the one that you want, then you have to go to the other side, that HA is the one that you want. Okay, so this curve means my HA. All right, if HA is correct, then my x bar should follow a normal distribution with this one is equal to, say, for example, if mu is larger than mu 0, it could be like 6, like we said before. I'll just take an example. Okay, so this is my mu A. Okay, so now I have my mu A here, a value which is larger than mu 0, but it could be anything. Okay, I just randomly say 6. It could be other values. All right, so this is my mu A. Now I have two curves. Okay, so if H0 is correct, then it will follow the left curve. If HA is correct, then the PDF curve of the second curve should be correct. Okay, and then we're going to find a critical value called C. For example, C is here. Okay, I will find a critical value here. And what we can obtain from the sample is the sample statistic. Here is the sample mean, right? Okay, so if this sample mean is larger than this critical value, okay, and we can have this corresponding probability. If this corresponding probability is small enough, what does it mean? It implies that this area is very small, right? So if this area is very small, it means the probability that x bar is larger than this critical value is super small, okay? But if H0 is true. But on the contrary, say I will change a color, okay? But on the contrary, if HA is true and you fix this critical value, what will happen? It means the red area is the corresponding probability that x bar is larger than C. You see what I'm saying? If you choose H0 as your ground truth, as the true stuff, okay, and you fix this critical value, which means, the green area is the probability that you will obtain an x bar larger than this, okay? So this probability is very small. But how small? We're going to discuss this later, okay? In this case, it's very small, so it's not likely to happen. For example, I'll just let this area to be 5%. So which means there are 95% that this one will not happen at all. Okay, so in normal people would say, okay, so I will not have a guess that, or we don't have enough evidence to prove that this one will happen. Okay. However, if you assume that alternative hypothesis is true, okay, and you fix this value, it means the probability that you observe a X bar is larger than this critical value is very large. Okay, so it's more likely to happen under the assumption of HA instead of under the assumption of H0. You see what I'm saying? So in this case, black. Okay, so in this case, this critical value C can help us to decide whether you reject the null hypothesis or not. Okay, if, sorry, okay, so this green area, okay, this green area is my rejection region. I'm going to use RR to denote the rejection region. Okay, if you observed X bar is within this rejection region, which is X bar is larger than C, it means the probability that your X bar is larger than the C is very small. It's not likely to happen. Even if it happens, like the probability is so small that we can ignore it. All right. Okay. In this case, if your observed sample statistic falls into this rejection region, I'm gonna, reject the null hypothesis and support the alternative hypothesis. Okay? However, if your observed sample statistic does not fall into the rejection region, what kind of conclusion can you draw from this? Can you say, okay, so I accept H0? Can I say this? Well, probably it's not a good idea. Why is that? Well, first of all, I will tell you my answer. I would say, okay, I fail to reject the null hypothesis. Okay, why did I say this? Because in general, you cannot prove something is correct. Okay, but on the contrary, it's much easier for us to prove something is wrong.